Good evening, students. This is S.Aravind, Assistant Professor, Department of DBSIT, Kavali. So, in the previous session, I discussed about introduction to the DC motors and then working principle of DC motors. In this class, I am going to discuss torque equation of a DC motor and power developed in a DC motor and next types of DC motors. So, firstly, I will start with the torque equation of DC motor. So, here, what is meant by torque? Okay, so torque is nothing but turning or twisting force about an axis, and torque is measured by the product of force and the radius at which the force acts. You know this one. So torque is measured by the product of force and the radius at which the force acts. So here I am taking one wheel. Okay, one wheel. So it consists of a radius r meters acted on by circumferential force F newtons as shown in the figure. If you observe this diagram, you will have the wheel in a circular shape, and we have one small circle is there inside this, that is the radius of the that wheel, and next we have some force acting on this one, that is F. So here I am considering this one, and then I am coming to, so here let the force capital F cause the wheel to rotate at n rpm. So here we are applying some force, that is capital F. So by using this, it is used to rotate the wheel at n rpm, that is the speed. Okay, so from that one, the angular velocity of the wheel is omega is equal to 2 pi n by 60 radians per seconds. Okay, so from that one I am writing torque tau is equal to F into R Newton meter. Okay, so from this one I am telling that work done per revolution. So here there is a formula for this one, that is work done per revolution is equal to capital F into distance moved. So here I am taking the force capital F into distance moved is 2 pi r joules. 2 pi r joules. So here r is the radius of the wheel. And next from this I am taking power developed, that is P is equal to, there is a formula for this one, power developed V is equal to work done by time. So work done by time, here I am taking the time, so that is equal to time required to complete a revolution, so that is equal to 60 by n. So here I am applying the formula to this one, that is in the place of n I am taking that 60 by n, that is f into 2 pi r by 60 by n. So from this one I am writing f into r into 2 pi n by 60. So from this one you know already torque tau is equal to force into radius. So that's why I am taking in f into r place I am taking torque tau. So here tau into 2 pi n by 60 watts. So from this one I am writing power developed P is equal to, you know already, omega is equal to 2 pi n by 60. So replace with omega by 2 pi n by 60, that is P is equal to T omega watts. So here tau is equal to torque in Newton meter and omega is equal to angular speed in radians per seconds. And next, the torque developed by a DC motor, actually the torque developed by a DC motor is obtained by looking at the electrical power supplied to it. So that is the input. Okay, the electrical power supplied to it, and mechanical power produced by it, this is the output. Okay, electrical power is the input and mechanical power is the output. So it is called armature torque. So the torque developed by a DC motor is obtained by looking at the electrical power supplied to it and mechanical power produced by it. It is called armature torque. So that is indicated with the letter, that is tau suffix A. So from this one I am writing the gross mechanical power developed in the armature is EB into IA. So here EB is the back EMF and IA is the armature current. So from this one I am writing mechanical power developed PM is equal to EB into IA. So here power in armature is equal to armature torque into omega. Okay, so in the power in armature place I am replacing with EB into IA, that is equal to armature torque, you know that is tau A into omega is, that is the angular velocity, 2 pi n by 60. Okay, and next, so here EB in a motor is given by, so I already said that in the significance of back EMF concept, here the back EMF formula is equal to the generated EMF in a DC generator, that is EB is equal to 5 PNZ by 60A. So in the place of EB, I am substituting the equation, that is 5P Z by 60A into, we have that is IA. So EB into IA, that is equal to tau A, that is the armature torque, into angular velocity omega. In omega place I am substituting 2 pi n by 60. So from this one I am writing tau A is equal to 1 by 2 pi into 5 into IA, that into PZ by A. So by solving the above equation, we have tau A is equal to 0.159 into 5 into IA into PZ by A Newton meter. So this is the torque equation of a DC motor. Okay, and next we have some other topics that are also here I am explaining. So here from that equation I am telling that torque tau is proportional to 5 into IA. That means here the torque of a given DC motor is proportional to the product of armature current and the flux. Okay, so here I am taking one more thing, that one shaft torque or useful torque. So shaft torque is represented by the letter tau sh. So here the torque developed by the armature is called armature torque. You know this one. So it is denoted as tau A. Here the full armature torque is not available for doing useful work. So here the full armature torque is not available for doing useful work. Here some amount of torque is used for supplying iron and friction losses in the motor. So actually these losses, iron and friction losses and copper loss, these are all I am going to cover in the coming topics. Okay, so here I am telling the only losses, that is some amount of torque is used for supplying iron and friction losses in the motor. Next, so this torque is called lost torque. This torque is called lost torque. It is denoted as tau suffix f. Okay, next, the remaining torque is available in the shaft, so it is used for doing useful work. Okay, so this torque is known as shaft torque or useful torque, and it is denoted as tau sh. So the armature torque is the sum of the lost torque, that is tau f, into shaft torque, that is the sum of lost torque, that is tau f, plus shaft torque, that is tau sh. So in the equation form I am writing tau A is equal to tau f plus tau sh. This is the armature torque. Okay, and next, so I am taking this diagram. So here I am taking, so if you observe this diagram, so we have motor with a pair of brushes, and next we have some parallel connection of inductor and some supply voltage V, and we have armature torque, that is tau A, and it consists of shaft torque and lost torque also. It is connected to the load. Okay, so from this one I am writing the output power of the motor is P out is equal to tau sh into 2 pi n. So here tau sh is a shaft torque. Okay, P out is equal to tau sh into 2 pi n watts. So from this one I am writing tau sh is equal to P out by 2 pi n. So here I am taking small n, that is where n is RPS, that is revolutions per second. So from this one tau sh is equal to P out by 2 pi n by 60. So here I am taking n in RPM, that is revolutions per minute. That's why I am taking n by 60 in place of small n. I am taking n by 60. So P out by 2 pi n by 60 Newton meter. So that is equal to 60 by 2 pi into P out by n Newton meter. So from this one I am writing tau sh is equal to shaft torque is equal to 60 by 2 pi. By solving this one we have 9.55 into P out by n Newton meter. Okay, this is the entire torque equation for a DC motor. This is the armature torque and shaft torque, and it is also known as useful torque also. Okay, this is the torque equation for a DC motor. And next, power developed by armature. Okay, so actually we know that armature current IA is equal to V minus EB by RA. So in the previous class I discussed about this thing, that is voltage equation, power equation and armature current. So from that one I am writing IA is equal to V minus EB by RA. So from this one I am writing V is equal to EB plus IA into RA. So if the equation is multiplied by armature current on both sides to the above equation, we will have the power equation. That is V into IA, that is equal to EB into IA plus IA square RA. So this is known as power equation of the DC motor. So from that equation, I am writing V into IA, that is equal to electric power supplied to armature, that is the armature input, and EB into IA, that is the power developed by armature, that is armature output. Next IA square RA. So this is the electric power wasted in the armature. This is the wasted power, that is loss. Okay, this is also called as armature copper loss, IA square RA. Okay, so from this one I am taking condition for maximum power. So actually we have the mechanical power developed by the is P suffix m is equal to EB into IA. So from this one I am writing now PM is equal to V into IA minus IA square RA. So here, since V and RA are fixed, that is supply voltage and armature resistance are fixed, power developed by the motor depends upon armature current. Power developed by the motor depends upon armature current. So for maximum power, I am taking differentiation to the power equation, that is for the mechanical power, that is with respect to armature current, that is dPm by DIA. So it should be 0. That means I am applying differentiation first to the mechanical power developed by the motor, and then I am taking this equal to 0. Okay, that is therefore dPm by dA into IA, that is equal to V minus, applying the differentiation to the above mechanical power developed by the motor. So while applying this differentiation with respect to IA for the mechanical power developed by the motor, we have V into IA. So differentiation of IA with respect to IA, it gives one value, that is V into 1 minus, by applying differentiation to the IA square with respect to IA, we have 2 into IA. So we have one formula differentiating the x square, it will give 2x. So applying this equation, this formula to this one IA square, we will have 2 into IA, that into RA. So this equation is equal to 0. From that one we have V minus 2 into IARA, that is equal to 0, or we will write this one like IA into RA, that is equal to V by 2. Now V is equal to EB plus IARA. So for that one I am writing EB plus, in IARA plus I am writing V by 2. Okay, V is equal to EB plus IARA, you know this one. In IARA plus I am substituting V by 2. That means VB is equal to V by 2. That is V is equal to EB plus V by 2. From that one I am writing EB is equal to V by 2. So hence mechanical power developed by the motor is maximum when back EMF is equal to half of the applied voltage. Okay, this is a note point, that is mechanical power developed by the motor, that is PM, is maximum when back EMF is equal to half of the applied voltage. So this is the power developed by the armature and condition for maximum power. And next, coming to types of DC motors. Okay, actually we discussed one topic in the DC generators also. We discussed about different types of DC generator. Likewise, here also we will discuss types of DC motor. So actually, types of DC motors is classified into two types, that is self-excited DC motor and separately excited DC motor. In self-excited, we have shunt motor, series motor, and compound motor. In compound motor also we have two types, that is short shunt compound motor and long shunt compound motor, and we will discuss in detail about these types of DC motors in the coming slides. That is, firstly I will take DC shunt motor. So here the motor, here the armature or the field winding is connected across the armature winding of the DC motor and to the supply. Okay, so from this diagram I am taking the shunt field current, that is ISH is equal to VT by RSH. You know the Ohm's law. So from the Ohm's law, I is equal to V by R. From that one I am writing shunt field current to this diagram, that is shunt field current I Vt by RSH. That is the Vt is the DC supply and RSH is the shunt field resistance. Okay. And next from this diagram I am writing armature current Ia is equal to, it is the summation of IL, that is the load current, plus shunt field current, that is ISH. So from this one I am writing IL is equal to, that is load current is equal to armature current minus shunt field current, that is ISH. That is IL is equal to Ia minus ISH. So from this one I am writing terminal voltage Vt is equal to EB, that is the back EMF, plus IARA, that is the armature drop, that is the IARA, plus brush drop, that is BD, brush contact drop. Okay, that is BD. Why I am not taking the shunt field current? The shunt field drop means, so here it consists of large number of turns and it consists of low current. That's why I am not taking this shunt field resistance, shunt field losses. Okay, fielding losses, that is Vt is equal to Eb plus IRA plus Bd. So from this one I am writing generated EMF or back EMF Eb is equal to Vt minus IRA minus brush contact drop Bd. And next from this diagram, power developed in the armature, that is equal to Eb into Ia or Eg into Ia. Okay, and power delivered to the load, that is equal to terminal voltage into load current, so that is Vt into IL. So that is equal to Vt into, we know that already IL is equal to Ia minus ISH. So substitute that one into this one. We will get Vt into Ia minus ISH. So you know already Ia is armature current, Ra is armature resistance, and Vt is terminal voltage, and IL is load current, and Bd is brush contact drop. So this is for DC shunt motor. And next I am going to DC series motor. So here, if the field winding is connected in series with the armature winding as shown in the figure. So if you observe this diagram, here the field winding, that is RSC, is connected in series with the armature winding as shown in the figure. So it is called DC series motor. Here the series field winding has few turns of thick having low resistance. Okay, so from this diagram I am writing the equations. So from the circuit, in this one armature current is equal to series field current, that is ISC, that is Ia is equal to load current, that is IL. Okay, so from that one I am writing Ia is equal to ISC, that is equal to IL. So from this one I am writing terminal voltage Vt is equal to Eb plus IARA plus ISC plus brush contact drop. So here Eb is the back EMF or generated EMF of the given circuit, plus IARA is the armature resistance drop, armature winding drop, plus ISC, that is the shunt field wind, series field winding drop, plus brush contact drop. Bd is the brush contact drop. So from this one I am writing Eb plus Ia into, actually from the series motor diagram we will write Ia is equal to ISC. So here I am substituting in ISC plus Ia. So from this one I am writing, I am taking common Ia. So for that one I am writing Ia of Ra plus RSC plus Bd, that is the brush contact drop, and generated EMF Eb is equal to, from the above equation, from the terminal voltage equation I am writing generated EMF or back EMF Eb is equal to Vt minus Ia of Ra plus RSC minus brush contact drop. So from the circuit I am writing power developed in the armature, that is equal to Eb minus Ia. Okay, and next input power, that is power delivered to the load, that is input power is equal to Vt into IL. So here IL is equal to Ia and that is equal to ISC. For that one I am writing Vt into Ia. Okay, so in the place of IL I am substituting Ia. Okay, since Ia is equal to IL in the series motor. Okay, you know that already, where Ia is equal to armature current, Ra is equal to armature resistance, Vt is equal to terminal voltage. Okay, so this is for DC series motor. And next I am taking DC compound motor. Actually Based on these field winding connections, the DC compound motors are classified into long shunt compound motor and short shunt compound motor. So based on the field winding connections, the DC compound motor are classified in two types. One is long shunt compound motor and another one is short shunt compound motor. So here I am taking firstly long shunt compound motor. Actually in a long shunt compound motor, the shunt field winding is in parallel with both series field and armature field winding as shown in the figure. So the armature winding as shown in the figure. So this is the diagram to the long shunt compound motor. So here I am taking shunt field winding and series field winding. Okay. So here the armature winding is connected in series with the series field winding and in parallel connection to the shunt field winding, and these all are connected across the load. Okay. So from this one I am writing from the diagram, shunt field current ISH is equal to VT by RSH. You know the Ohm's law. So from the Ohm's law, I is equal to V by R. So shunt field current ISH is equal to VT by RSH. So for the DC compound motor, that is the long shunt compound motor, armature current or IA is equal to IL plus ISH. Okay, or IA or IS is equal to IL minus ISH. That means here for the long shunt compound motor, IA is equal to ISC. So for that one I am writing in the IA plus ISC, that is IA or ISC, that is equal to IL minus ISH. So from this one I am, from the diagram I am writing terminal voltage VT is equal to EB plus IARA plus ISC RSC plus brush contact drop. So from that equation I am writing generated EMF EG or back EMF EB is equal to VT minus IARA minus ISC RSC minus brush contact drop. So you already know that IA is equal to ISC from the diagram. That means I am substituting in place of ISC IA. So from that one I am writing VT minus from these two IARA minus ISC RSC. So from these two I am taking the common factor as IA. So I will take IA common, that is IA of RA plus RSC minus B into, that is brush contact drop BD. So from this one I am writing power developed in armature, that is equal to EB into IA. So from this one I am writing input power VT into IL, that is equal to VT into in IL plus I am writing IA plus ISH, that is armature current plus shunt field current. So where IA is equal to armature current and RA is equal to armature resistance and VT is equal to terminal voltage and IL is equal to load current. So this is for long shunt compound motor. And then coming to next one, that is short shunt compound motor. Okay, so actually in a short shunt compound motor, the shunt field winding is connected in parallel with armature winding. Okay, in a short shunt compound motor, the shunt field winding is connected in parallel with the armature winding. Okay, and then to the series field winding also. Okay, and these all are connected across the load. Okay, so this is the diagram to give clarity about the short shunt compound motor. And next from this diagram I am writing series field current. So from this diagram, series field current ISC is equal to IL, so that is equal to IA plus ISH. So for a short shunt compound motor, series field current, that is ISC is equal to load current IL. So this is the load current is the combination of armature current and field current, that is the shunt field current. And next armature current IA is equal to, from this one I am writing IA is equal to ISC minus ISH. So from this one I am writing terminal voltage VT is equal to EB plus IARA plus ISC RSC plus brush contact drop. So from this one I am writing generated EMF or back EMF EB is equal to VT minus IARA minus ISC RSC minus brush contact drop. So from this one, power developed in the armature is equal to EB into IA. So here input power is equal to VT into IL. there is a terminal voltage into load current. So where IA is equal to armature current, RA is equal to armature resistance, VT is equal to terminal voltage, and IL is equal to load current, and BD is brush contact drop. So these are the different types of DC motors we have. Okay, thank you. That's all for today. And in the next class, I am going to discuss some more topics from the DC motor concept. Okay, thank you.